So let me also start with thanking our organizers. This is indeed my first time to Europe. As a consequence, this will be my very first talk in Europe. So thanks the organizers very much for giving me this opportunity to give my first European talk in this very city of this very fabulous season. So I will start with some preliminaries and background. After that, I will present our results and discuss some main ideas behind the proof. So in this talk, we'll be concentrate on two important geometrics associated to a bounded pseudoconvex domain in CN. One is the Bergman metric, the other is the complete Kähler-Einstein metric. So let's start with briefly recalling their definitions. So to define Bergman metric, we need to first recall the Bergman kernel. Let omega be a bounded domain. We know that the Bergman kernel is defined in terms of the A2 space, which is the space of L2 integrable harmonic functions on the domain. And if we let phi case be the orthonormal basis of A2 space, then we can define the Bergman kernel as the infinite sum in terms of phase. Alternatively, we can define the Bergman kernel as the reproducing kernel of A2 space. If once we have the Bergman kernel, which we denote by K of the bounded domain omega, then we can define the Bergman metric in the following way. We take the I d by log of the Bergman kernel, which is a Hermitian 1-1 form, because we assume the domain is bounded. As a result, this Hermitian 1-1 form will always be positive definite. So the induced metric the introduced one is a metric. And an important property of the Bergman metric is that it is canonical. That is, it only depends on the complex structure of the domain. More precisely, if we have two domains, omega 1 and omega 2, which are biholomorphic by the map F, then F preserves the Bergman metric of the two domains. So that's the Bergman metric. So for Kähler-Einstein metric, so let's say we start with a complex manifold M equipped with a Kähler metric G. So in local chart, we can write G as a Hermitian matrix, let's say Gi, Gjk, and being Kähler means that locally we have a potential function, phi. And the Ricci curvature of this metric is defined as the minus d bar log of the volume form, or the determinant of the metric. We say it's Kähler-Einstein if the Ricci curvature is proportional to the metric by a constant lambda. And this constant lambda is the so-called Ricci constant. And by the work of Cheng and Yau and a subsequent work of Mok and Yau, we have the following fact. On a bounded domain, omega, it admits a complete Kähler-Einstein metric if and only if it is pseudoconvex. So that gives another calculation of the pseudoconvexity. The existence of complete Kähler-Einstein metric is equivalent to the pseudoconvexity. Let me also put a couple of remarks. Under our setting of bounded domains, if it's Kähler-Einstein, then there is Ricci constant. Lambda must be a negative number. And the second remark is that the complete Kähler-Einstein metric G is indeed unique up to scaling if we further insist that this constant lambda to be -1, then it is unique. Then there's no more freedom of scaling. It becomes unique if we insist that this constant to be -1. The last remark is that this complete Kähler-Einstein metric we post that Ricci constant -1, such complete Kähler-Einstein metric is canonical, only depends on the complex structure. Again, it means that if we have a biholomorphism F between two domains, omega 1 and omega 2, and if they are both convex, so that the complete Kähler-Einstein metric exists, and we assume to be Ricci constant -1, then F preserves such Kähler-Einstein metrics. Yeah, exactly, yeah. Now we have two canonical metrics which both depends only on the complex structure. One is Bergman metric, the other is complete Kähler-Einstein metric. Then a natural question is, when do these two canonical metrics coincide? And it's natural to ask this question on bounded pseudoconvex domains because the existence of complete Kähler-Einstein metric requires pseudoconvexity. So when do they coincide? It's maybe a good time to pause to give an example. Let's take the simplest model of pseudoconvex domain, let's say the union ball. We know that it's routine to check and compute that the Bergman kernel of the union ball is given by this, from which we can compute the Bergman metric. And also it's well-known fact that the Bergman metric of the union ball is indeed hyperbolic or has constant holomorphic section curvature, which is stronger than being Kähler-Einstein. So this means that in particular, on the union ball, at least, we can say the two canonical metrics coincide. The Bergman metric coincides with the Kähler-Einstein metric, at least on the ball. Is that the only case? No, actually more generally, these two canonical metrics always coincide on bounded homogeneous domain. That is to say, if omega is a bounded homogeneous domain, being homogeneous means that the biholomorphic automorphism group of the domain acts transitively. Then we always have the two canonical metrics coincide. That is, the Bergman metric is Kähler-Einstein, and this fact can be proved by using a simple application of the Bergman event function. So what is that? Let me elaborate. So recall the Bergman event function is defined as follows. So we start with the bounded domain omega as k to be the Bergman kernel. So this d bar log of k is going to be the Bergman metric. Let capital G be the volume of the metric, of the Bergman metric, or the determinant of the Bergman metric. Then the Bergman invariant function associated to this domain omega is defined by this. To emphasize, it depends on this omega, domain omega, we write as B sub omega, defined as the quotient of the volume G, or the determinant G over the Bergman kernel. What is nice about this Bergman invariant function is that the following invariant property observed by Bergman, this Bergman invariant function is called invariant function because it is invariant under biholomorphisms. That is, if F is a biholomorphism between two domains, omega and omega 1 and omega 2, then the Bergman invariant function are equal at point Z and the image point FZ. In particular, if I have a homogeneous domain omega, then I can say this function is constant because for fixed Z, I can by taking appropriate F, I can make FZ to be any point. So it's constant. So let's pause to give an example. We know that the union ball is homogeneous, and one can compute it is a constant, first of all, and one can compute the constant is this constant. We also know the Pauli disk is homogeneous. So for a Pauli disk, the Bergman invariant function should also be constant, and one can compute the constant is this. And this actually gives another proof of that the union ball is not biholomorphic to the Pauli disk in several complex variables, because if they were biholomorphic, then they must be equal. However, they are not equal. Okay, let's come back to our setup. Our setup is that if omega is bounded and homogeneous, and we have just convinced ourselves that the Bergman invariant function is constant. Recall the Bergman invariant function is defined by the quotient of G over K, where G is the volume of the Bergman metric. So we have this is G is proportional to Bergman kernel at every point by the same constant C. If we take minus d bar log of both sides, then the right-hand side is precisely Ricci, by definition of Ricci. And for the right-hand side, because we take d bar of log, this constant C goes away, and it is precisely the definition of Bergman metric up to a minus sign. So this is precisely the definition of being Kähler-Einstein with Ricci constant -1. So what we have convinced ourselves on this slide is that if we assume the domain is homogeneous, then the Bergman metric is Kähler-Einstein, or the two canonical metrics we are interested in coincide. Are homogeneous domains are the only ones? Are there any other domains these two canonical metrics coincide? So that leads to a conjecture of Yau in the early 80s. Yau conjectures that's the only case. Yau conjectures that the Bergman metric of a bounded pseudoconvex domain is Kähler-Einstein if and only if the domain is homogeneous. So we have just convinced ourselves that the backward direction is easy because it just follows from Bergman's observation and the Bergman invariant function. The challenging part is the forward direction, that is, assuming the Bergman metric is Kähler-Einstein to prove or to disprove the domain is homogeneous. That is the difficult part, and it's still widely open. And that will be the main interest of this talk. In several complex variables, we know that in general, it could be very, very difficult to understand the geometry of a domain if we don't know much about the boundary in several complex variables. So why not? Let's start with the special case where we assume the domain has smooth boundary and the boundary is strongly convex. In this case, for this case, actually a conjecture was posted even earlier by Cheng in the late 70s. The conjecture that the Bergman metric of a smooth bounded pseudoconvex domain, strongly pseudoconvex domain, is Kähler-Einstein, then it must be biholomorphic to involve. I want to emphasize that this Cheng's conjecture is a special case of the Yau's conjecture. Why? Suppose the Yau's conjecture is true, then by Yau's conjecture, this domain omega must be homogeneous. Then by a theorem of one, who proves that if we have a smoothly bounded strongly convex domain, if in addition is homogeneous, then it must be biholomorphic. So if we use one result, we can tell Cheng's conjecture is a special case of Yau's conjecture, because in this case, being homogeneous is the same to say being biholomorphic unipolar. Okay. So what are the results on a special case of strongly convex? So what's the result on Cheng's conjecture? A remarkable step toward understanding it was done by Fu and Wang, and then Rosk and Shavikov. Combining their result, we can tell that the Cheng's conjecture holds in two-dimensional case. And more recently, with Huang, we prove that Cheng's conjecture holds for higher dimensional case. So that means by the above work, this special case of Yau's conjecture, the strong pseudoconvex case of Yau's conjecture, which is the Cheng's conjecture, holds. If we have a smoothly bounded strongly pseudoconvex domain, the Bergman metric is Kähler-Einstein if and only if it's biholomorphic to involve. Before we discuss more general cases of Yau's conjecture, let's try to understand the ideas behind the proof of Cheng's conjecture to get some inspirations. So the key ideas in the proof of Cheng's conjecture can be summarized into a couple of steps. The first step is to first study the geometry of the boundary. So we start with the assumption is that these two canonical metrics coincide. The Bergman metric is Kähler-Einstein. And from that, we can get some information on the asymptotic behavior of the Bergman kernel, from which we then derive some CR geometric information on the boundary. And the key goal is to show the boundary is spherical. That's a very rough summary of the idea in step one. And in the next slides, I'm going to elaborate on this step one. So the key thing is to study the geometry of the boundary by using the Kähler-Einstein assumption on the Bergman metric. Recall that we have this celebrated Pfefferman expansion of the Bergman kernel if omega is strongly convex, where rho is a defining function of the domain, where here we assume it's positive in the interior, and phi and psi are smooth functions in a closure of the domain. In the case, in the two-dimensional case, the key idea is to look at so from Pfefferman's expansion, we can see the Bergman kernel possesses two types of singularity. One is log singularity, one is the rational type singularity. To approach Cheng's conjecture in two-dimensional case, the right idea is to look at the log singularity term, that is this psi term. And from the Kähler-Einstein condition on the Bergman metric, one can show that this psi vanishes to the infinite order along the boundary. And that then leads to the so-called Raman-Dolov conjecture, which asserts that if this psi is precisely this coefficient in Fefman's expansion, the conjecture asserts that if psi vanishes to the infinite order, then the boundary is spherical. And in C2, is correct by the result of, it is confirmed by the result of Burns-Graham and independently by Budman-Weil. However, this conjecture is much less understood and is widely open in higher dimensions. But at least it works in two-dimensional case. From the Kähler-Einstein condition, we can say psi vanishes in the order. And by the solution of the Raman-Dolov conjecture in C2, we can say the boundary is spherical. So that finished the first step in two-dimensional case. Yeah, I'm talking about on this, all strength at this moment. I'm going to move to more general context later, yeah. So that's complete this step, or complete proving the boundary to be spherical in the two-dimensional case, in the proof of Cheng's conjecture. In the how about higher dimension, how about 3 and higher dimension, technically one can also follow this strategy by the same proof. One can still show psi vanishes to infinite order along boundary, even in higher dimension. In any dimension, you can show psi vanishes to infinite order. However, then if we follow this path, one have to study the Raman-Dolov conjecture in higher dimension, which appears to be very difficult. So this might not be the realistic approach for Cheng's conjecture in higher dimensions. In higher dimensions, instead of looking at the psi term, the more doable approach is to look at this singularity, the rational type singularity, or the strong singularity term, that is to look at phi. From the Kähler-Einstein assumption on the Bergman metric, we can get some information on phi. And what is nice about phi is carries the information of Chern-Moser CI curvature tensor. From that information, one can show the Chern-Moser tensor vanishes along boundary. That means every boundary point is CI umbilical, so the boundary is spherical. Let me again summarize the idea by comparing them. So the key thing is to use Fefman's expansion of the Bergman kernel together with the Kähler-Einstein condition. In two-dimensional case, for hypersurface in C2, we know that to check the CI umbilicity of a boundary point, we need to look at the 6th order Cardan's curvature tensor. And Cardan's curvature tensor is encoded or is carried by psi. In higher dimension, we know that to check whether a boundary point is CI umbilical, we have to check whether the Chern-Moser curvature tensor vanishes or not. And that information is carried by phi. Then, in these two different cases, we respectively use the Kähler-Einstein assumption to examine psi and phi respectively. In the two-dimensional case, we show by using this Kähler-Einstein assumption that Cardan tensor vanishes at every boundary point. In the higher dimensional case, we examine phi to show the Chern-Moser tensor vanishes at every point. Then every boundary point is CI umbilical by definition, and by the well-known Chern-Moser normal form theory, the boundary is spherical. So that's the first step. We have to treat the two-dimensional higher dimension differently to show the boundary is spherical. And step 1, study the geometry of the boundary. In step 2, we have to come back to study the geometry of the domain. Now, what we have in hand is the boundary is spherical. Maybe I should have explained what is spherical, but it was already explained by Ilya in his talk. Spherical means that the boundary is locally CI equivalent to a sphere at every point. If we know the boundary is spherical, then by a uniformization theorem of Lemurowski and Shavikov, we know that the domain is covered. The universal covering of the domain omega is the unit ball. Once we know that, then because the hyperbolic metric of the unit ball, or the Bergman metric of the unit ball equivalently, is invariant on the biholomorphism of unit ball. So that's hyperbolic metric descends down to the base, to the downstairs, because it's covered by unit ball. Then on the as a downstairs omega, we have two Kähler-Einstein metric. One Kähler-Einstein metric is a Bergman metric because we assume it to be Kähler-Einstein. The other is this hyperbolic metric. Hyperbolic means it has constant holomorphic segment curvature, which is stronger than Kähler-Einstein. So we have two Kähler-Einstein metric. And by the uniqueness of the Kähler-Einstein metric, they are the same. What that means is the Bergman metric is hyperbolic. Or the Bergman metric has constant holomorphic segment curvature, and then using that and a uniformization theorem of Cheng-Yau, then we can immediately conclude that it's biholomorphic to the unit ball. So that's the second step. But in this talk, we're actually going to concentrate on step one. Okay, now what we all discussed is only about strong pseudoconvex case. So we have convinced ourselves that the Yau's conjecture in the special case of Yau's conjecture of strong pseudoconvexity case had been settled. That is, the Cheng's conjecture has been solved to prove to be true. Then it will be natural to investigate Yau's conjecture for, say, finite type pseudoconvex domains, and this could be a priori be much more difficult to start with. In general, even for the notion of finite type, we have two different notions. One is D'Angelo's notion, one is the commutator notion due to Kohn or Bloom and Graham. It will be a question of which notion would be easier to deal with in this setup. But let's, again, refresh our memory about the Yau's conjecture. The Yau's conjecture says that on a bounded pseudoconvex domain, the Bergman metric is Kähler-Einstein if and only if it's homogeneous. And now we are interested in the smoothly bounded and finite type case. And I would like to remark that by an extension of Rosset of one theorem, the original statement of Rosset says this: if we have this so-called boundary orbit accommodation point is smooth and strong pseudoconvex, you just need one such boundary orbit accommodation point to be smooth and strong pseudoconvex, then the domain is biholomorphic to unit ball. And if this domain, if Yau's conjecture is correct, then this domain is homogeneous. Homogeneous means every boundary point is a boundary orbit accommodation point. And we know that for a bounded, smoothly bounded domain, there must exist a strong pseudoconvex boundary point. Then there must be a boundary point which is strong pseudoconvex and which is also a boundary orbit accommodation point. Then this means if we use Rosset, it must be biholomorphic to the unit ball. So that means if Yau's conjecture holds for any smoothly bounded pseudoconvex domain, if Yau's conjecture holds for any smoothly bounded pseudoconvex domain, then we should have the following effect. That is, the Bergman metric of a smoothly bounded pseudoconvex domain is Kähler-Einstein if and only if the domain is biholomorphic to the ball, because that follows from Rosset, homogeneous is equivalent to biholomorphic to the ball if the boundary is smooth. So second? Yeah, it only requires the boundary to be smooth, because if the boundary is smooth, there always exists at least one point to be strong pseudoconvex. Right? You just pick any point inside and choose the furthest point. As the furthest point will be strong pseudoconvex. Right. Okay, so it would be nice if one can find an approach to prove this last statement of Yau's conjecture for smoothly bounded pseudoconvex domains, but as we mentioned, this appears to be very difficult because we don't know much about the boundary if we are too ambitious to work on this statement. So instead, we're going to consider Yau's conjecture for finite type domains. And we said we already reviewed the solution of strong convex case of Cheng's conjecture. And in strong convex case, let's review this strong convex case to get some inspirations. In strong convex case, there are two fundamentally important tools that were used. One is Pfefferman's expansion of the Bergman kernel. And secondly, this expansion of the Bergman kernel, this coefficient psi and phi, is ultimately connected with the CI invariant theory of the boundary. So if we want to use an analogous approach for the finite type case, then one should ask, can we generalize 1 and 2 to finite type case? There are actually some successful generation of 1 and 2 to weakly pseudoconvex case. For example, for the Bergman kernel, there has been study of the follow-up rate of Bergman kernel on weakly pseudoconvex case, for example, by Osawa and by Katzny and many other people. For example, normal form theory on weakly pseudoconvex case, there has been work of Martin Kohler, Evenfeld, and more recently by Kosowski and Zaltsev. However, on the other hand, because of the more complicated geometric nature of finite type domains, one cannot expect the result, these tools to be as nice as strong pseudoconvex case, and the picture in a more general context of finite type is less clear and appears to be very difficult to apply to approach this Yau's conjecture. As a result, little progress had been made toward understanding Yau's conjecture in this more general context of finite type case. And to my best knowledge, in this more general context of finite type domains, the only result that was known was due to Fu and Wang. They proved that they have to pose first of all, they consider in domains in C2. A nice thing would be you don't need to worry about a different notion of finite type because the two different notions coincide in C2. They have to first, they additionally assume it's complete Reinhardt. Then they should, if it's smoothly bounded, complete Reinhardt, pseudoconvex of finite type domain in C2, then Yau's conjecture holds. That is, if these two metrics coincide, if and only if it's biholomorphic, unible. If it's in C2 and if it's complete Reinhardt. And their proof utilizes the limit of the Bergman invariant function we just introduced along transversal paths approaching the boundary. And moreover, their proof need to estimate some very complicated integrals, and they use the aid of programming, again, reflecting the complexity of the problem in this more general context of finite type. And very recently, together with Savali, we were being able to confirm Yau's conjecture for all two-dimensional finite type pseudoconvex domains. So that means we remove the complete Reinhardt assumption. So we have proved that if D is a domain in C2, which is mostly bounded pseudoconvex of finite type, then Yau's conjecture is true on such domains. That is, if the Bergman metric coincides with Kähler-Einstein metric, then it must be biholomorphic to unible. And in the remaining time, I'm going to talk about some key ideas behind the proof. But before that, I probably should also mention a corollary of the theorem. That is, if instead of assuming it's smoothly bounded, if we assume it has real analytic boundary, then boundedness plus real analytic would imply it's finite type. Then we would have finite type and pseudoconvex. Then we can apply the theorem so that in particular, for bounded pseudoconvex domains where with real analytic boundary, we can say Yau's conjecture is true. If Bergman metric coincides with Kähler-Einstein metric, then it's biholomorphic tunable. So in the remaining time, I'm going to talk about some ideas behind the proof. So of course, the key role in the proof is again played by the asymptotics for the Bergman kernel. Recently, in 2020, for two-dimensional pseudoconvex domains, Xiao and Savali, they obtained the asymptotics of the Bergman kernel along transversal paths approaching the boundary for two-dimensional pseudoconvex domains of finite type. If you pick a transversal path toward the boundary, then they obtained the asymptotics along that path. Unfortunately, this is not suitable for our proof of Yau's conjecture. Instead, for our proof, we shall need to extend the asymptotics result to tangential paths. We will not be able to use transversal paths to prove our theorem, but we have to work with tangential paths approaching a boundary point. Furthermore, more importantly, these paths had to be chosen to be critical tangent. What do I mean by critical tangent? This means the order of tangency with the boundary must be equal to the type of the point that's being approached. So maybe I should make a picture. So omega is a smoothly bounded pseudoconvex domain of finite type in C2. I mark any boundary point, that's called the star, let's say it's of finite type R. What Xiao and Savali was interested in is the Bergman-Kernel expansion along a transversal path, like alpha here, transversal path. However, in our work, what we are interested in is a tangential path, that's called gamma. It is, furthermore, chosen to be critical tangent, which means the tangent order equals to the type R. And with such choice of tangent path gamma, we can prove that the Bergman kernel along such tangent path gamma have the following asymptotics, where rho is a local defining function, where we assume to be positive in the interior at nearby the boundary point that we marked the star. It will be interesting to compare this expansion with Pfefferman's expansion. So Pfefferman's expansion is, we are in C3, right? That's only right is for, sorry, C2. That's only right is for C2. Then this will be a cube. This will be a log term. This is Pfefferman expansion for strongly pseudoconvex. It only works for strongly pseudoconvex domains in C2. The first main difference between Pfefferman and this expansion is that Pfefferman's expansion holds at everywhere in omega. Our expansion only works if we restrict to this path. It only has this expansion along that path. And moreover, if you choose different paths, gamma, there's not, of course, not only one choice of path to be critical tangent to the boundary point. If you choose different gamma, then you would end up with, in general, you would end up with different numbers, coefficients, aj and bj. It depends on the path you choose. So that's the difference. So the first difference between Pfefferman and this expansion is the type. And that's what I'm going to say. In Pfefferman expansion, you can see this is 3. Here, we would end up with some fractional power, where I is the type. Yeah, but as we said, the coefficient will be different, but the format should be the same. Yeah, right. And why we choose, and similar thing would hold if you take derivatives for a derivative of Bergman kernel, and why we choose this critical tangent path. The important reason is this. With this carefully chosen path, it allows us to make use of the leading coefficient, A0, to analyze the local model of the domain. What do I mean by that? So I'm coming to the next page to explain that. So omega is a finite type pseudoconvex domain in C2. We've marked a point, the star, at the boundary of finite type R. At this point, the star, we know that after change of coordinate, we can assume this point is the origin, and omega is locally defined by, say, the imaginary part of W greater than P plus some higher weighted order terms. Here, P is a homogeneous real polynomial of degree in Z and Z bar with no pure holomorphic or anti-holomorphic terms, which equivalently to this. Then the local model for omega at this point, the star is this. That is, what do I mean by local model? The key thing is that if we choose that very special critical tangent path gamma, this leading coefficient A0 in the expansion picks up the most amount of information from the Bergman kernel of the model. That is, we can roughly speaking, we can compute this A0 more or less in terms of the Bergman-Kernel model. If we still use the transversal one, then you still have such very similar expansions. Very similar expansion still holds. However, if we stick to the transversal path, this leading coefficient A0 would pick very limited information about the model. So that's about the transversal path. You might ask, then why you choose the tangent path to have the tangent order equal to be R? If we choose the tangent order to be greater than R, then we cannot prove it. We will not be able to prove this, first of all. If we choose tangent order to be less than R, it still picks less information from the model. Yeah. Actually, if it's still convex plus finite type, then at a generic point, it's strongly convex. At a generic point, it's always finite type. The difficulty is how do we deal with this thin set of weakly convex point, right? No, this point holds at a finite type point, weakly convex point.
Suppose you only have it.
Yeah, that's not. You can only show the strongly convex boundary point is spherical. But what can you say about the bad point? I mean, how do you know it's not this? A generic point, boundary point, is spherical. But there are some finite. How do you deal with that? That's a very difficult problem. Although it's a thin set, but that's the essential challenge of this problem. Okay, so with this carefully chosen critical tangent path, the leading coefficient pick up the most information from the model, and we are going to use that. The Kähler-Einstein condition can imply a Ming-Xiao type equation for the Bergman kernel, and then by using the asymptotics of this Ming-Xiao equation along that gamma, we can derive some condition on the Bergman kernel of the local model of the Bergman kernel of this guy, from which we show this P must take the following form. So the type will be 2M. And once we have that, then P is very explicit. We just plug in to compute and use again this Ming-Xiao type equation again. We can prove M can, we're gonna get some, if we look at the most singular term at the asymptotics, we're gonna get some combinatorial equation about M or about R. And then we prove that combinatorial equation only have one solution, which is R equals 2. So once we have R equals 2 means the type is 2. Type is 2 means it's strongly convex. Then it is reduced to the strongly convex case, which is Chen's conjecture C2, which is already confirmed by Fernwang and Nemirovsky and Shavikov. Thus we are done. So what we have proved is really the following. To summarize, what we have proved is if a smoothly bounded finite type circumference domain in C2, if it's not strongly convex, then the Bergman metric cannot be Kähler-Einstein. That's really what we proved. I think I finished early. Thank you very much for your attention.
Which we're not trying to do.
Right.
But you were trying to study behavior.
Right. You can say that, but only probably along some fixed path. Yeah.
Take those eight.
Exactly. Yeah, that's exactly what we do here. But it appears difficult, and the most easy case is to relate A0 to the geometry. What do we exactly?
Zero, right?
Yeah. Right.
Zero.
Right. Exactly.
It
Yeah.
seems to me that in general,
Right.
being able to say new information about the Bergman kernel, interpreting those eight.
Exactly. That's how people did in the strongly convex is to interpret the psi and the phi in the expansion with the CI invariant, like the Kähler tensor to model tensor, and the ambitious goal would be also to interpret this AJ and BJ with some canonical choice of a defining function, with the geometry of the boundary, geometry of the boundary. It is very appealing, but very difficult, it appears to be. Yeah. No, I don't. I'm not. Yes, we tried. Yeah, but his approach is so. Well, the starting point of his is different. So he would fix with a different kind of P and study it. Yeah, it's quite difficult. I also thought about this, but it appears to be difficult. Yeah, that's a very good question.
So if you take the polynomial model, how many coefficients?
I see. I think only the leading. Yeah, as far as we can compute, it's only the leading coefficient is 0. Yeah, and also even for this one, we have to choose this very special tangent path to recover the information.
Only the leading term depends only on the polynomial.
Yeah, I should say I don't know. As our method shows, only the leading coefficient. Yeah, right.
If you try to prove it in CN, and you try the same expansion.
The problem is we don't have the same expansion.
Do you have any expansion in CN? And what's that?
Right. That's a very interesting question. So even independent of Yau's conjecture, people would be wondering what's the analogous of Pfeffer expansion in finite type case, whichever sense it is. But that also appears to be very difficult. And only recently, they proved for C2 finite type. Only very recently. Yeah. Yeah, but for transversal paths, yeah. Oh, yes. Sure. I mean, if and only if it's pseudoconvex, right? Yeah, this one, yeah. Yeah, they actually prove for more general even Stein domains, but if we apply their theorem to our setup, then it's it. But the question is whether we can drop the boundedness. I think we can relax it, but I'm not sure whether we can complete the job. Yeah. Yeah, because you can scale it. Originally if it's k, if you scale it by m, then be k divided by m, for example. Yeah. Yeah, apart from that's unique. That follows from Yau's Schwarz lemma. Yeah.